First of all, dear everyone, myself Dr. Vanika, Assistant Professor in Ajay Kumar Gar Engineering College, Ghaziabad. So today I am going to discuss the topic of Engineering Mathematics second, and the topic is linear differential equations of nth order with constant coefficients. So the linear differential equations with constant coefficient is the equation of the form A naught nth derivative of y with respect to x n plus a1 n minus 1 1th differentiation of y with respect to x n plus a2 n minus 2th differentiation of y with respect to x and plus up to plus an y is equals to q. Here y is the dependent variable which depends to very independent variable x, and a naught, a1, a2 up to an all are constants, and q is the function of x only. Now let us assume that d by dx is equivalent to capital D. So therefore d2 upon dx2 is equivalent to d square, and up to dn upon dxn is equivalent to d power n. So the equation 1 is converted as a naught d power n plus a1 d power n minus 1 plus a2 d power n minus 2 and plus up to an into y is equals to q. Here this is the function of d, so we can write fd into y is equals to q. So according to the theorem, the solution of this equation is equals to the y is equals to the u is equals to v, where u is the complementary function of the equation f dy is equals to 0 and v is the particular integration of the equation f dy is equals to q. So the complete solution of this equation is equals to complementary function plus particular integral. So in order to solve f dy is equals to q, first we find complementary function, that is complete solution of f dy is equals to 0 and particular integral of f dy is equals to q. So now consider the differential equation as equation 1 f dy is equals to q. Complementary function is the solution of equation 1 when its right hand side is equivalent to 0. So f dy is equals to 0. So now find complementary function. First we obtain auxiliary equation of the equation second by replacing d by m and y by 1. So the auxiliary equation is f m is equals to 0. Now we have to find the roots of this auxiliary equation. So complementary function of the equation depends on the roots of the auxiliary equation. So here some cases arises. Now case 1, if real and distinct root. So now firstly we will assume that the roots of this equation is m1, m2, m3 up to mn, and in first case we consider roots, all roots are real and distinct, and then the complementary function of the equation is equals to c1 e power m1x. This term is for root 1 m1 and plus c2 e power m2x, for root 2 m2 plus c3 e power m3x for third root, and plus up to plus cn e power mnx for nth root mn. Now for case second, if two roots m1 and m2 are equal, so the complementary function for equal roots is equals to c1 plus c2 into x e power m1x. If three roots are equal, so terms will be c1 plus c2x and plus c3x square and e power m1x. And now for other roots, plus c3 e power m3x plus c4 e power m4x and plus cn e power mnx. Now for example, we have to solve d cube y upon dx cube minus 7 dy by dx minus 6y is equals to 0. So firstly we will assume that d by dx is equivalent to operator capital D, and then d2 upon dx2 is equivalent to d square, and d cube upon dx cube is equivalent to d cube. So equation will be replaced in this form: d cube minus 7 d minus 6 into y is equals to 0. So now to find the auxiliary equation, we will replace d by m and 1 y by 1. So the auxiliary equation is m cube minus 7m minus 6 is equals to 0. Now factorize this equation: m plus 1, m plus 2, m minus 3 is equals to 0. So roots are m is equals to minus 1, minus 2 and 3. So all three roots are real and distinct. So a complementary function for this equation is equals to c1 e power minus x for root 1 minus 1 and plus c2 e power minus 2x for root minus 2 and plus c3 e power 3x for root 3. Now since here the function q is equals to 0, so particular integral is equals to 0. Now the complete solution of the given equation is CF plus PI, so is equals to C1 e power minus x plus C2 e power minus 2x and plus C3 e power 3x. Now next example is we have to solve dq minus 5d square plus 8d minus 4 into y is equals to 0. So to find the auxiliary equation, we will replace d by m and y by 1. So the auxiliary equation is m cube minus 5m square plus 8m minus 4 is equals to 0, and factors of this equation are m minus 1, m minus 2 whole square is equals to 0. So roots are m1, 2 and 2. Here two roots are repeated. So for repeated case, the CF will be C2 plus C3 into x and e power 2x, and for root 1 term will be C1 e power x. So the complete solution of this equation is equals to y is equals to CF plus PI. Here since function q is 0, so PI will be 0. Now here case third, when two roots of auxiliary equation are imaginary, let m1 is equals to alpha plus iota beta and m2 is equals to alpha minus iota beta. This root is conjugate to this root, and all other roots m3, m4, m5 all are distinct and real. So for imaginary roots, the term of CF will be e power alpha x and into c1 cos beta x plus c2 sin beta x and plus c3 e power m3x for real roots. These terms for imaginary roots and these all are for real roots, and plus up to cn e power mn x. Now for fourth case, when roots of auxiliary equations are repeated and imaginary roots, now let m1 is equals to m2 is equals to alpha plus iota beta and m3 is equals to m4 is equals to alpha minus iota beta. This root is conjugate to this root. So now for these imaginary roots, the terms of CF will be e power alpha x. Since here two roots are equal and then m3 and m4 are equal, so terms will be c1 plus c2x cos beta x and plus c3 plus c4x and sin beta x plus c5 e power m5x for real root and plus up to plus cn e power mnx. All these terms of CF is for real roots. And now case fifth is when roots of auxiliary equations are irrational, and for let us assume m1 is equals to alpha plus under root beta and m2 is equals to alpha minus under root beta. Then complementary function for irrational roots is e power alpha x c1 cos hyperbolic under root beta x and plus c2 sin hyperbolic under root beta x. And for real roots, the terms are plus c3 power m3x plus c4 e power m4x and plus up to cn e power mnx. Now we have to solve the differential equation d power 4 plus 8d square plus 16 into y is equals to 0. So now to find the auxiliary equation, we will replace d by m and y by 1. So the auxiliary equation is m power 4 plus 8m square plus 16 is equals to 0. So this is the whole square of m square plus 4, and then the roots will be plus minus 2 iota and plus minus 2 iota. So plus 2 2 iota is repeated twice, and minus 2 iota is also repeated twice. So here now the complementary function for this equation is e power 0x, because here the real terms is 0 and here also the real term is 0. So now c1 plus c2x cos 2x and plus c3 plus c4x sin 2x. So now the value of e power 0x is equals to 1. So the complete solution is equals to c1 plus c2x cos 2x plus c3 plus c4x sin 2x. Now we have to solve this differential equation. D square plus 1 whole cube and into d square plus d plus 1 whole square y is equals to 0. So now to find the auxiliary equation, we will replace d by m and y by 1. So the auxiliary equation is equivalent to m square plus 1 whole cube and into m square plus m plus 1 whole square is equals to 0. So the auxiliary the factors of auxiliary equations are m is equals to plus minus iota. Now plus iota root is repeated thrice, because here m square plus 1 power is 3, and now minus iota repeated thrice, and m is equals to minus 1 plus minus iota and root 3 by 2 is repeated twice. Now the for these roots, the complementary function is e power 0x, and for root plus iota minus iota repeated thrice, the complementary function term is c1 plus c2x plus c3x square and into cos x plus c4 plus c5x plus c6x square into sin x, and for these roots the term is e power minus x by 2 for real terms, and now for imaginary terms c7 plus c8x cos under root 3 by 2x and plus c9 plus c10x sin under root 3 by 2x. Now this table represents the complementary function according to the auxiliary equation roots. If one real root alpha 1, then the complementary function will be c1 e power alpha 1x, and if two real and different roots alpha 1 and alpha 2, then complementary function will be c1 e power alpha 1x plus c2 e power alpha 2x. And now if two real and equal roots alpha 1 is equals to alpha 2, then the complementary function will be c1 plus c2x e power alpha 1x, and if three real and equal roots alpha 1 is equals to alpha 2 is equals to alpha 3, then complementary function will be c1 plus c2x plus c3x square e power alpha 1x. And if one pair of imaginary roots is alpha plus minus iota beta, then complementary function will be c1 cos beta x plus c2 sin beta x. Here beta is the imaginary part of the root and into e power alpha x. Here alpha is the real part of the root. And now if two pair of equal imaginary roots alpha plus minus iota beta and alpha plus minus iota beta, and for repetition case the complementary function will be e power alpha x c1 plus c2x into cos beta x and plus c3 plus c4x sin beta x. And here c1, c2, c3, c4, all these are arbitrary constants. Now next example is we have to solve the differential equation d square y upon dx square plus y is equals to 0 with the boundary condition at 0, y at x is equals to 0 is equals to 2 and y at x is equals to pi by 2 is equals to minus 2. So firstly we will replace this equation in form of capital D operator. We have to assume d by dx is equivalent to capital D. So here equation will be d square plus 1 into y is equals to 0. Now to find the auxiliary equation, we will replace d by m and y by 1. So auxiliary equation will be m square plus 1 is equals to 0. So roots of this equation is plus minus iota. So complementary function, because these roots are imaginary roots, so complementary function will be c1 cos x plus c2 sin x and into e power 0x, because here the real part of the root is 0. So now value of e power 0x is equals to 1. So complementary function will be c1 cos x plus c2 sin x. Since here the function of q is equals to 0, so pi will be 0. So now the complete solution of the given equation is equals to cf plus pi is equals to c1 cos x plus c2 sin x. Now, by applying the given condition, y at x is equals to 0 is equals to 2, we will put x is equals to 0 and y is equals to 2 in the equation 1. Then we will find c1 is equals to 2. Now applying the second boundary condition, we will put x is equals to pi by 2 and y is equals to minus 2 in this equation. Then we will find c2 is equals to minus 2. So now put the value of arbitrary constant c1 and c2 in the equation 1. Then the complete solution is equals to 2 cos x minus sin x. This is the particular solution, because in this solution we does not here no arbitrary constant exists. So now these are some practice questions and these are some reference books for engineering mathematics second. Thank you.